All right. Just make sure I'm recording and audio's on. We're good. All right. I'm sure you are all very excited, or I don't know if it's excitement. I'm sure you all want your exams back, and I will provide them for you, but we're going to wait till the end of class. And I know I've walked into that before, and I'm just, oh, you know, come on. But I really need to make sure that I get through today's lecture. And if I start talking about this, I know I'm going to eat up way too much time. So I'd rather limit myself at the end to how much I can talk. Right? So you will get these back, and we will talk about, you know, where we go from here. All right, but today we move on. All right? We are done with 2.2. We now move into 2.3, basic differentiation formulas. And I told you before that we get to a point in Cal 1 where the limit goes away, at least for a little while. Okay, the limit's going to go away. We will revisit the limit, but this whole thing that we did on the last test, we have now a super shortcut to do all that work. And here are the rules, and there's a bunch of them, all right? And there's even more. A lot of these appear on your formula sheets. Does anyone have their formula sheets with them? Yeah. I can tell you what page it's on. There we go. So there's a sheet here. It's reference page.
Oh, there it is.
Reference page 5, differentiation rules, and it has all these rules here on differentiation. Please be aware of those rules. All right? Thank you. So what I'd like to do is just go through each of these rules. I'm going to give you an example or maybe several examples of each rule until I feel like we've got the idea. And then after we're done with that, I'm going to try and go back and prove some of these rules to try and show you why these rules are true. All right? So let's start with the first one. The derivative of a constant is 0. So the first rule says that the derivative of c, which is a constant, is equal to 0. And I think this is obvious. Let's see. Let's see if it is to you. If I take a function, which, by the way, this is the function we're talking about. If I say, hey, we have some function, f of x equals, let's say, 5. That's a constant, right? If we graph this, it's just a horizontal line, right? It's flat. And it goes through a y value of 5, like this. And to say that we want to know what the derivative of it is means you want to know the slope of the tangent line, right? Well, if you pick any point on this curve and look at the slope of the tangent line there, it's what? 0. And it doesn't matter where you are on that curve. It's always flat. So does that make sense that it would be 0, no matter where you are? Okay. Done. Derivative of a constant is 0. So let me give you another kind of example. What if I write this as an example? Find the derivative, or I'm going to write it this way. Let's take pi, e to the pi prime. So e is a number, isn't it? Mm-hmm. Yeah. E raised to the number pi is a number. So a number raised to a number, that's just a number. That's a constant, right? It's not as nice as 5, but it's a constant. Agreed? And so the derivative of this should be 0. And that's it. We're done. All right, next rule. The derivative of x. Let me make sure I've got the right rule here, that I'm doing them in the right order. Yeah, derivative of x. So the derivative of x is 1. Now, I'm using this notation that we did discuss last class. This means, hey, take the derivative, x is your variable, of what? Of that function x. So it says that the answer is 1. Let's try and justify it with a picture. What does that function look like if we call this function right here f of x? This is one of those important functions from college algebra. F of x equals x. It's called the identity function. And if I draw it, it is a line, right? But it's that perfect diagonal, isn't it? Slope of 1. So if I go to that line and I pick any point on that line, anywhere, and ask you for the slope of the tangent line, it will be parallel to the line, won't it? And the slope of that line is 1. So that means the slope of the tangent line should also be 1. Agreed? Visually, makes sense? Okay. All right, so I'm not going to say any more about that. That's pretty straightforward.
Even if you change the rate of the slope.
Well, we're saying the derivative of x by itself, right? Now, if I say what's the derivative of 5x, now it's going to be a little different, but we will address that. Okay, the next one. This is the big one. This is the big one for today. So big, in fact, that I'm going to write what it's called. It's called the power rule. And you'll hear me say that a lot. Okay, look, we're going to take derivative. Just use the power rule. Just use the power rule. I'll just say that. This is what I'm referring to. And here's what it says. The derivative of x raised to the n power is equal to nx to the n minus 1. That's the derivative. Now, I gave you some, I kind of, remember when we were cheating a while back and I said, hey, there's going to be a shortcut later, right? Here's the shortcut, here's the rule. Let's see this rule applied to a problem. Let's say you have x to the 7th power and you want to take the derivative. According to this rule, n is what? 7, right? So we're just going to take that n. We're going to write the n out front, 7. Then we're going to write x to the 7 minus 1, which will give us 6. So 7x to the 6th. And that's your answer. That's it. Isn't that a lot better than the limit? Right? It's a lot quicker than that limit is, right? Now, I am going to prove this to you, okay? When I go back at the end of this, we're going to come back and prove this, because this is too big of a rule for you to just take it on faith. Like, oh yeah, sure, that works. You know, who cares why? How about this one? Can you use the power rule here?
Yes.
Yes, as long as this is x to a power, right? Which it is. So I'm going to rewrite it first. Notice I'm keeping the prime. I'm writing x to the 1/2 prime. And now n is 1/2. So you must bring the 1/2 out front, right? And at this point, I'm not going to write the prime anymore, right? Because I'm actually applying the rule. 1/2 comes out front. And then x raised to the 1/2, and I'm going to take 1 away from that. And so you're going to need to be comfortable with arithmetic with fractions, okay? Keep it as a fraction.
So
negative 1/2. So this is 1/2 x to the negative 1/2.
In that case, would you write it as 1 over 2x squared?
Yeah, so let's talk about the different ways we could write it. This would be okay, all right? But some people might complain that, you know what, you shouldn't leave negative exponents. So you might say, okay, well, that's equal to 1 over 2x to the positive 1/2, right? Dropping that x to the negative 1/2 down, it'll join the 2 that was already down there. And then some other people might say, no, I want to go even further. I'd like to take it back to what it is. And look, x to the 1/2 is a root. So they might even go as far as that.
And then it'll be like, oh, well, I don't like the radical underneath there.
It's perfect. It's everyone's personal preference. But in this class, I recommend, I thought I had red markers. Okay. Here's what I recommend, everyone. This. I'm erasing everything because I really want to stress that this is going to come up again. star, star, star. We'll make this a 4 star, okay? The derivative of the square root of x is equal to 1 over 2 root x. That was the final version that I wrote over here, right? There are some things that you just have to memorize in math classes, right? The Pythagorean Theorem, a squared plus b squared is c squared, right? In a calculus class, this is one of those ones that you just want to have memorized. The derivative of the square root of x is 1 over 2 root x. And just automatic, without doing any work. Is there a question? You look,
no question.
Okay. Oh, any clarification needed? No? All right.
That makes it easy for all the other roots, right?
What's that?
That would make it easy for all the other roots.
The other roots don't work that way, unfortunately. Nope. But this one comes up a lot. We take the derivatives of square roots a lot in calculus. So it's good to just know that it's just going to be 1 over 2 root x. And you move on. All right, so let's try a new example. How about this one? Ooh, ooh. This one's giving me bad goosebumps. That's your test question. That a strong majority did not get correct. This was, I believe, number 15? No, number 14. Find the derivative of 1 over root x. And you had to use the limit definition, and had a lot of people, the one h goes to 0. I had a lot of people not get this. In fact, we will look, and we will look at exactly how many people didn't get it. But let's try and do it the easy way now, with the power rule. Well, first of all, we have to be able to write this as x to a power. Right now, it's not quite, right? So I'm going to make this 1 over x to the 1/2, right, like that. Now, this is still not written as x to a power. This is 1 over x to a power. So you must have x to a power, not a fraction. So how can I make that just x to a power? Bring it up as a negative, right? So now I'm going to write this as x to the negative 1/2. That's just properties of exponents, right? There's nothing new there. Bring it up. Now does it look like this, x to a power? Your power is what? Negative 1/2. So you're allowed to use the rule. The negative 1/2 is going to come out front. So I write equals, negative 1/2 comes out front, x to the negative 1/2, and I need to subtract 1 from that. Negative 3/2. Don't be using decimals here. Don't go to your calculator to do negative 1/2 minus 1/2. Just, I'm only going to show this one time because this is calculus. So common denominator, turn that 1 into a negative 2 over 2. Negative 1 minus 2 is negative 3 over the common denominator, negative 3/2. All right? So this is going to be negative 1/2 x to the negative 3/2. Or you can drop it down. Really, I don't care. I don't care. The advantage to having something like this is that if we were asked to find a second derivative, we would just go from right here. We would just go to it. Because you actually have x to a power again, and you could repeat the process. But if you go do all that moving around and then ask for the derivative again, you're going to have to move it all back to this. So there's pros and cons. It just depends on the context of the problem. All right. I do want to write it the other way just so you can get used to it. I can write that as negative 1 over 2 x to the 3/2. Notice on my fractions, sometimes I write 3 with a straight bar over 2, and sometimes I write 3 with a slashed bar over 2. That's something wrong with my wiring, and I've never been able to fix it. I just switch back between the two depending on how much space I gave myself. It bothers me. It really bothers me, but I can't do anything about it. All right, there we go. Got it? Now I can do back to radical notation if I want. There's nothing wrong with it to do that. Negative 1 over 2. I could write that as a square root of x cubed, couldn't I? And I could even go further than that, because when you take the square root of x cubed, you can actually pull 1x out of that, can't you?
Yeah. Should be 2x.
So this is negative 1 over 2x root. What was still under that root? The single factor of x. That was the answer on the test. If you got it right, you'll remember that. I'll hand these back. You can take a look at them. So I would claim that that's a lot easier, right? Well,
No, I was saying, I got it right, but I was like, but I think I forgot the negative.
the negative. If you forgot the negative, I didn't take off much. But I would have circled. What you did was forgot to distribute through a negative up top when you were doing the h. You'll see. Okay. We good? Make sense? All right. Just out of curiosity, what's the derivative of x again, everyone? 1, right? I wonder if this power rule works even here. Like, because this is x to what? First power? So let's try to use this rule. The 1 would come out, x to the 1 minus 1, right? So 1, x to the 0, but x to the 0 should be 1.
So 1 times 1 is 1.
So 1 times 1 is 1, so that is 1. Hey, the rule works here. Now, we don't need to do it that way. I would encourage you to just know the derivative of x is 1. We good? All right. How about this? Why don't you try this one on your own? What's the derivative of 1 over the cube root of x squared? See if you can do that one. What, the fraction? Radical? We have this property. That's your property of exponents that we use to convert from a fractional exponent to a radical notation. The denominator is the root and the numerator is the power. This will go further. Yeah. Okay. You'll get faster and faster doing this subtraction. You'll get faster and faster the more problems you do. I remember when I was first learning Cal 1, you know, I was having trouble going quickly from here to here, you know, like I was writing it down and doing it in common denominator. It's fine. The speed will come, but speed won't come if you don't practice. No. Okay, I just put it up here so you could look through it. Any questions on any of the work? We're all okay? All right.
It's okay if we leave it as the second to last step, right?
This is okay, this is okay, this is okay, this is okay. I'm okay with all of those. But be comfortable, though, changing from, I'm not requiring any of these specifically because they're not, they're all equivalent. So no one of them is more right than the other, but you should be able to move from one version to the next. All right, power rule. Awesome rule. Okay, it's going to save our, you know what? Yeah, time also. All right, so let's take a look at the next rule. The next rule is what we call the constant multiple rule. And it is important, but it's not the power rule, all right? The power rule is the big daddy one today. All right, this constant multiple rule. Now the notation here is a little confusing, so I don't want us to get bogged down with the notation. It says if you have a constant times a function, right? So you're trying to take the derivative of a constant times a function, not a constant by itself. What's the derivative of a constant by itself? 0, right? We already talked about that. But if that constant is attached to some function of x, here's what you do with the constant. You just bring it out. It's almost like factoring it out. And then what you do is you say it's that constant times whatever that derivative of the function is. You'll hear me say it this way. The derivative of a constant times a function, the constant's just going to come along for the ride, all right? And we're going to differentiate the function and then slap the two back together. All right?
So
That's it.
it's like 5x.
Yeah, that's what I'm going to start with. I'm going to do something like that. I'm going to use that rule in conjunction with the power rule right now. So if we want to take the derivative, I'll use this notation right now, of 10x to the third, right? I don't need the prime. Sorry, I'm saying derivative already. Then we notice that we have a constant, right? Attached to a function through multiplication. So that can pop out as a 10, and then I'm just going to do the derivative of that power function. Right? So the 10's going to come along. I kind of changed notation on you here, sorry. 10's going to pop out, and then just find the derivative of that. What is the derivative of x cubed? 3x squared. Right? 3x squared. So you'll have 10 times 3 times x squared, and of course 10 times 3 is 30. 30x squared. And we're done. We okay with that? I'm going to do another one right below it. What if we have 1/2 x to the 10th and I want the derivative? So we could just do this the same way, right? Write the 1/2 on the outside and then take the derivative. But really, at the end of the day, what's happening is that the constant's coming along for the ride, right? So I like to just kind of cover it up. It's going to come along for the ride, and then I say, what's the derivative of x to the 10th? What is it? 10x to the 9th. And I'm going to multiply that times 1/2. So it's going to be really 5x to the 9th, right? I'm actually writing the step down here. But if I were doing this problem for real, I wouldn't even write the 1/2 times 10. I would go straight from here to here, because I'd realize 10 hits the half, half of 10 is 5, and then x bring the power down 1. Yeah? Yeah, this is nice, right? All right, let's do another one. How about this? Take the derivative of 4 times the 4th root of x to the 3rd. Yeah, you can go ahead. See if you can figure it out. That's just a reminder to myself. What would you do first here if you're working this one out? That 4 can come out, right? What about this ugly thing right here? Convert it to x. So we call this right here radical notation. We call the other notation rational exponents. Rational meaning fractional exponents. Just so we have the proper language. So 4 times x to what? 3 over 4. And now I'm ready for the derivative. I have a constant that's attached to a function through multiplication, so it's going to come along for the ride. The 3/4 is going to pop out. So if you can do that in your head, great. If not, just write it down. X to the 3/4 take away 1. And I hope that this multiplication is easy for you. We have 3x to what? Negative 1/4. Which could, you're done at that point. You could write that as this if you wanted. Drop it down, then take it back to a radical. It's your call. Does this seem pretty straightforward? Okay. I know you wish that your test was like 8 of those, right? Yeah, except you had to use the limit. Okay, so look. On this one, we have a new rule. The sum and difference rule. If you look back at everything we've done so far, everything I've taken a derivative of has been a single term. Right? It's been like the constant function. F of x was 5. Or we took derivative of x. X is just one term. We did x to various powers. That's a single term. Terms are separated by addition and subtraction. The question is, if you have two functions that are added or subtracted together, how do you take their derivative? Well, fortunately for us, all you have to do is take the derivative of each one separately. So if you have two terms, added or subtracted, and you want to know the derivative of that, just do each one separately, get the answers, slap them together, and you're done. It's nice and clean. All right, so here's an example. Find the derivative of 5x cubed minus 3x to the 6th. So let's see how quickly you can move through this now. You have two terms, right? So that means I can take derivative of each one separately. What is the derivative of 5x cubed? 15x squared. Right, 3 comes out, hits the 5, that's 15. Take the power down by 1, you got 15x squared. All right, 15x squared. Then minus, right, because this is a minus right here. Now take derivative, cover up that minus. What's derivative of 3x to the 6th? 18x to the 5th. Right? Done. That's it. Yeah, don't go setting this equal to 0. I mean, that's not what we're being asked to do right now, right? Just find the derivative. All right, how about this? Take the derivative of 4 root x plus 1/3 x to the 7th minus 4 pi. How many terms do you see? 3, right? 1, 2, 3. So I can take the derivative of each one of them separately. 4 root x. 2x and negative 1/2. Now, that you can do it that way. Nothing wrong with that. Fine. The way I would do it is just cover up the 4 because it's going to come along, right? What's the derivative of root x? 1 over 2 root x. 1 over 2 root x. 1 over 2 root x. Right? That's the one you just want to automatically know. 1 over 2 root x times 4. So I have 4 times 1 over 2 root x. I'll cancel those out, and that'll give me my 2 over root x. Now, what about the next one? 7, right? You're going to have plus, and then this comes out 7 times a third. 7 thirds. That's what it is, right? X to the 6th minus 0. You know what sometimes gets people? Is if I'll put on here like 4, like pi squared. That'll get people. Right? Because what will people want to do here? They'll drop the 2 out and they'll reduce the power by 1. But guess what? Pi is not x. Pi is a number. This is all a constant, isn't it? And the derivative of a constant is 0. So there's nothing else. It's all gone. Understand? Question?
So that'll
Sure.
be your answer? You don't have to-
That's it. Yeah, you don't have to put minus 0.
We could leave it as the 2x to 1.
Yes, you could. Oh, wait, I'm sorry. This isn't simplified. We could go a little more here. This goes in there twice. You could do that. Yeah, that would be more correct.
Does it matter where you put the x? Because I put 7x to the 6 over 3.
No, that's fine.
Okay.
The question here is, could you write 7x to the 6th over 3? That is correct.
Because if you multiply that out, that's where it
That's right. These are the same. These are the same. Now, back in college algebra, a lot of times we would write this and this would be an answer. But as we start to get more into the calculus, we start to realize that this number out front, 7 thirds, really does not play a part in the derivative. It just comes along. And what we're more interested in is in that part. So that's why a lot of people, as they move on, stop writing things this way, because it's just not as useful as that is when you take derivatives. Does that make sense? Because if I ask you to take derivative again right here, you drop your 6 out and then power down by 1, right?
is. That one you got.
This one you might have a little trouble with. What's that 3 and okay, it doesn't matter. Same thing. It's correct. All right, how about this one? How about negative 3x to the negative 2 minus 1/2 x to the negative 1/2. I'm throwing a bunch of minuses in here just for fun. Minus 5x to the negative 4. Yeah, that's good enough.
We should put some more negatives in this.
Yeah, just to be safe. We put enough negatives in, it'll become positive, right? Something like that. How many terms do you see? 3 terms. 1, 2, 3. I look at this one. I have a constant times x to a power. Good. Constant times x to a power. Good. Constant times x to a power. Good. So I can handle all these, can't I? On this first one, I'm just going to hide the negative 3 for now. Derivative of that, negative 2 comes down, right? That negative 2 is going to multiply and hit that negative 3, which will become positive 6 x to the negative 3. Be very careful there. You have to subtract 1 from negative 2, right? Negative 2 take away 1 is negative 3, not negative 1. So this is 6 x to the negative 3, right? Next one. This right here. Come out, hit this. What's negative 1/2 times, you can look at this as a negative 1/2. What's negative times a negative going to be? Positive. 1/2 times 1/2? 1/4. So you get positive 1/4, so I'm going to put plus 1/4. And then the power comes down. Subtract 1 from negative 1/2. Negative 3/2. X to negative 3/2. And then, lastly, plus 20 x to the negative 5. Good. So it may take you some time doing the homework to write out the details and start to get comfortable with this. But you do want to get to a point where you can do it all in one line like this and just almost mentally walking through it. Okay? Any questions? Sure? I get the sense that y'all get this. I mean, yes? You're like, yes, I can do this. Huh? What about it? Well, yeah, remember I said I'll accept this as an answer. There's nothing wrong with this. I could drop it down as, and then change it to a root. Same with this one. You could argue that. You could drop that down as an x cubed. All right.
If you want to take another derivative.
That's right. If you want another derivative, it's probably best to keep it exactly the way it looked right there and go again. All right, how about this? I mean, it doesn't look like I've added anything new here, right? All over x squared. Now that's different, okay? Because although I agree with the idea that this is a power of x, this is constant times power of x, constant power of x, constant power of x, constant power of x, nowhere in our rules did it say that if we had division in our function, that we could just do each one of them separately, right? Never said that. It just said x to a power, we're good. It said constant in front of x to a power, we're good. Adding two terms together, differentiate each one individually, we're good. Division, nothing yet, right? No rules yet. That comes next class. But there is still a way we can do this, just using some algebra first. Notice that we have 3 terms in the numerator and 1 term in the denominator, right? If you have 1 term in the denominator, you're allowed to split this up, right? Into 3 separate fractions. This is not any calculus yet. I'm just going to rewrite this as 3x cubed over x squared. And then how do you want me to write the next one? You want to write minus 4 root x over x squared. That okay? Then plus 2 cube root of x over x squared. I want that derivative, don't I? Okay. Well, you now have 3 terms. Are each of these x to a power? Yes, but we have to actually convert them into those, right? It's x to a power over x to a power, so we need to simplify that first. Like, what's x cubed over x squared? Just x, right? Go back to college algebra when we did like simplification here. We're going to be using this rule from college algebra, or even before that, I don't know, depends on where you saw it. X to the m over x to the n is x to the m minus n. That if you have x to a power over x to a power, you subtract the powers. That's what I'm going to do all the way across. But before I do that, I'm going to write it out again. I'm going to get rid of those radicals. Right, 3x cubed over x squared. I'm going to write minus 4x to the half over x squared. And then plus 2 what? X to the 1/3 over x squared. All I did was converted all my radicals to rational exponents so that I could apply this rule. This is not, I said rule. Don't confuse. This is not a differentiation rule. This is a law of exponents, right? I still have my prime arc. I have done no calculus yet. All right, x cubed over x squared, that's a pretty clean one, right? 3 minus 2 is 1. And your answer, whatever that you get here, always, no matter if it's positive or negative, is going to start off being in the numerator. So I'm going to have 3x to the first power, which I don't need the 1, do I? No, I don't need it. Okay, now the next one. Minus 4, that's going to be this part. Now you have to do 1/2 and take away 2. 1/2 minus 2? Negative 3/2. And what I was just saying, that your answer has to be on the top, x to negative 3/2, like this. That's what that one is. You see what I'm saying about these fractions? See that? Like, I don't get it. I just can't stick to the same thing. I don't know. I have not found a pattern to it yet. Yeah, don't focus on my issues. You don't want to be like I am. All right. What about the next one? Plus 2, right? And then x to the, what is it? Negative 5/3, right? You're doing 1/3. You're taking away 2. So that's 1/3 minus, you need the same denominator, 3, so this is minus 6 over 3. 1 minus 6, negative 5, negative 5/3. I still haven't taken a derivative. This is just making it look so I can take a derivative. And now I just do power rule on each one. What about this first one? I can cover the 3 up, right? If I want, I can ignore it, and I'm going to bring it with us in the answer. Derivative of x is 1. So that's going to be 3 times 1, that's just 3. So we get 3, so that equals 3. All right, how about this? This is a little weird. Negative 4, this power is going to come out and hit it.
That's going to be positive 6.
Yeah, maybe I'll write it out. I'm going to write it. Negative 4. I'm going to be multiplying that times negative 3/2. And then it'll be x to the negative 3/2 minus 1. I'm writing this one out in some detail. All right, so that became the 3 in front. This negative 4 was here. The negative 3/2 came out. I subtract 1 from that. This one will be plus 2 times the negative 5/3 comes out, x to the negative 5/3 minus 1. Y'all get it? And this should clean up. Don't ever leave your answer like that. These two numbers have to multiply together. Actually, you can include that negative in there. What's that? Plus 6. So 3 plus 6, x to the negative 5/2. And then these two together, minus 10/3. Just leave it like that. Don't put 3.333. Keep fractions alive, okay? 10/3 x to the negative 8 over 3.
Is it just because that they are exacting numbers?
Yes. Yeah, this is why in like a college algebra class, you're encouraged to not turn things into decimals all the time. Because when you get here, like what if you wanted another derivative, you know, you would come out with this, what if you had turned that to a decimal? Then everything's going to start becoming decimals. Decimals are approximations, and you're going to start to create a lot of error. The more times you go to decimals, more likely the more you're going to have problems with your answer, not being accurate. Not to mention, if we ever have to set it equal to 0 later and factoring with decimals is tough. So. All right, that's our answer. Got it? All right, good. This is a nice section, okay? This section, there's no craziness. There's really not a whole lot that we need to stress out about. The bad news that not much of this is going to be on the test in terms of, like, you're not going to have like 5 of these problems on the next test. This stuff is embedded within the other problems. This is automatic. You have to be automatic to be able to do this. Am I making sense? This will be like trivial, kind of. So, yeah. But we need to cover a couple of other things in this section. Hold on. There are some derivatives, okay, that we're just going to provide for you, and you just need to know them. Now, I can prove these to you, and depending on how much time I have left after I do the proof of the power rule, I might show you this one, and then maybe offer one of these as a bonus or something. All right? But everyone, let's do this as a class. Let's do it like we'll chant it, all right? Everyone, the derivative of sine of x is cosine x. Hardwired into your brain. Don't ever forget that. The derivative of sine x is cosine x. All right? And it's kind of cool because if you look at the graph of sine, there's sine. What's the slope of the tangent line right here at 0? What's the slope of that line look like? Looks like it's 1, right? And it turns out that what's the value of cosine there? 1. What's the slope of the tangent line right here on sine? 0. And actually that's at the same place. That's at the same place that cosine is 0. And then what's the slope of the tangent line right here on sine? It's actually -1. And that's the value of cosine there. And so if you graph cosine here, along with sine, you can see that, I hope you can see, that whatever this tangent line is doing corresponds to the height of the cosine function. So like down here, tangent line is 0. Well, look, cosine 0 there. If I move to the right, the tangent line is becoming positive, and so is the cosine function is becoming positive. So the derivative of sine of x is cosine x. Now, the derivative, it would be great if the derivative of cosine was just sine, because then there wouldn't be a lot to remember, right? They're derivatives of each other like that. But there's a little catch. The derivative of cosine is negative sine. And I think you can see it if you just look at the blue curve now as the curve we're looking at. And let's look at the tangent line there. What's the slope of the tangent line right here on the cosine curve? -1. What's the value of sine there? +1. What's the slope of the tangent line right here on the blue curve on cosine? +1. The value of sine is -1. It would be nice if that was up here and this one was down here. And then if you draw sine upside down, which is negative sine x, then it would match the slopes on cosine. So if you don't follow any of this, just remember those, okay? And then, well, guess what? There were 6 trig functions, weren't there? Well, here you go. The first 3 you should memorize. I know you have your formula sheets. I know that I tell you you can use them on the test, but you do not want to walk into another class and need that formula sheet for the derivative of the first 3 trig functions. Your teacher will have a very bad opinion of you if you have to go reference what sine of x is, what derivative of sine of x is. All right? So let's, derivative of sine of x, cosine x. Derivative of cosine x, negative sine x. Derivative of tangent x. Secant squared x. That's weird. I will prove these to you later, not today. I am going to prove the number 6, but not all these. Derivative of cosecant x. Negative cosecant x, cotangent x. Okay. Derivative of secant x. Secant x, cotangent x. The last one is cotangent, and the derivative of cotangent is negative cosecant squared x, which you just have to memorize them. Not all of them. First 3 for sure. The other ones, well, try to do it. This one, I think if you're going to pick priority list, sine, cosine, tangent, and secant are the ones you should try and memorize. The others don't come up as often.
Is it because we don't study them as often? Or?
No, it actually has to do with certain techniques that we use in Cal 2. And in these techniques, those four trig functions are utilized the most in trying to do something later that we're trying to accomplish a task. Those four trig functions are most widely used for these techniques that we use. It's kind of hard to put, we're putting a carriage in front of the horses here. It's hard to see the forest through the trees right now. You just have to trust me that some of them are used more than others. All right, are you ready for some proofs? I know you're just happy with the rule and you could just live with that, yes, and not need any proof. But those are some very important rules in calculus. So let's see how we arrive at these rules. Let's take a look at, let's show that the derivative of x to the n is equal to nx to the n minus 1. Let's show that. Because I told you that, and you believe it now, and you love it, right?
Yeah.
Love is a word I can use for that?
Great.
Okay, it's great. All right, so let me go back and let me try it with the definition. The definition of the derivative. The derivative of x to the n should be the limit as h goes to 0 of f of x plus h minus f of x over h. That is the generic formula for the derivative of a function, right? That's 2.2, section 2.2. Now, for us, the function we're dealing with is x to the n. So if you need to, I'll write it up here for you. The function we're working on right now is x to the n power. So what I want to do is I want to plug into this, into that function, for x, I want to replace it with what? X plus h, right? X plus h in there, then subtract f of x, which is itself. So it should look like this. X plus h to the n minus x to the n all over h. Agree? Now, x plus h to the n power is not x to the n plus h to the n, right? No, right? We know this? Right? Look, a lot more students would pass college algebra if that's the rule, if that was the rule, because this is one of the biggest mistakes that they make, right? If you have something that, look, on your test you just took, you had to do a limit where it was 3 plus h cubed minus 27, or was that your class or the other class? Over h, okay, so you had to do that, right? So you had to do 3 plus h cubed, and that took a little work, right? This is going to take a little work too. X plus h to the n. So we talked about Pascal's triangle. We mentioned it, right? And I said that there would be a day that I talk about it. I've been waiting on it, and today's now time to talk about Pascal's triangle. All right, so let's put this on hold for a second. Okay, right now, I'm holding here because I don't know how to deal with this. I need to find a way of somehow getting my head around what that is. If somebody told me squared, I'd be in business, right? I just squared. If they gave me cubed, I would do it and I'd be done, right? But the problem is n. It's not given to me, right? So how could I ever expand it if I don't know what the number is? Well, we actually won't need to, and you'll see why. All right. So we're holding off on that idea right now? All right, here we go. What is x plus h to the 0 power? 1. So I'm going to write this like this. I'm going to say equals, and then way out here, I'm going to write 1. And don't worry too much about why I went way out there and wrote 1. What is x plus h to the first power? X plus h, right? just itself. I'm going to write it like this. X plus h. What's x plus h squared?
X squared plus 2xh.
So that you would have to FOIL it and put it together and get all that stuff and combine like terms. And I think, yes, no, maybe not. Maybe I assume too much. I don't know. I think we've done that enough where you could at least agree with me that that's what that would turn out to be. All right, now cubed. Cubed you did have to do at least one time. This turns into x cubed plus 3x squared h plus 3xh squared plus h cubed. So that's what you would get if you cubed it. Now, at this point, you have to kind of just believe me, if you don't know what's going on here, that that's true. Then x plus h to the fourth would be x to the fourth, 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the fourth. Of course, right? That's what you do. That's what you get, of course, when you multiply x plus h 4 times together. Come on.
Really?
We all knew that, right?
Of course, Professor.
Yes.
Of course you did.
Are you silly?
So when I'm doing this right now, in my mind I have 5 sets of parentheses and I'm distributing through, okay? I'm doing it in my head and I'm getting x to the 5th plus 5x to the 4th h plus, what do you mean? You can't tell me what I'm thinking.
Doing something with the last.
No, I'm not. I'm not doing any, I'm doing it in my head. Hold on, I need to concentrate, please. Stop confusing me. Okay.
Oh.
Yes, that was it. There's a pattern, right? There's a pattern. So let's talk about the pattern. What's happening is, first look at the x's. Look at each of these rows and just look at the x's as you go from left to right. What happens in every single row with the x's as you move from left to right? Did you say increase or decrease? The x's?
No, I meant like.
No, I'm not talking down this way. I'm talking each row, each row, each row, each row. Look at the x's as you move from left to right. I start out with what? X to the 5th, the next one, 4th, 3rd, squared, first power, gone. That happens on every single row. What about the h's? It's opposite, right? If I move from left to right, it's opposite. No h's, h squared, h cubed, h to the 4th, h to the 5th, right? And that number, 5, actually matches up with that number, doesn't it? This 4 is that 4. And same with the last ones, right? 4, 4, 5, right? So if I were going to write the next one, here's what I could tell you so far. The first guy right here should be what? X to the 6th. And I know that the last one should be h to the 6th. That's what should happen. Then all this middle stuff, I don't know. I haven't talked about the numbers, have I? I haven't talked about the numbers yet. But we can at least talk about the letters. So I'm going to leave a blank spot here. I know that this would be x to the what? 5. And I'm going to have an h there, right? And I just keep moving across. I know I'm going to have a number here, right? And then it's going to be x to the 4th h squared. And I continue this all the way across until I get all my x's to go down, all my h's to come up, right? Maybe we can actually identify what this number would be. Do y'all see a pattern?